Okay, with this agenda, the general cutting plane method, so the principal idea, sorry, and then different classes of cutting planes, which generally fall into two categories. And just as node selection was the stepchild of the branch and bound algorithm, cut selection will be something that we talk about briefly here in the end, because it's also important, but not as important as the procedure of generating the cuts. So, motivation cutting planes, besides from doing it as a complete algorithm, which will actually be the first part after this introduction, why do you use cutting planes inside a branch and bound algorithm? Well, the original MIP formulation that a practitioner, a user, a modeler gives to a solver can almost always be improved. And by improved, I mean many different things, but in particular, getting a smaller difference between the space of feasible continuous and feasible integer solutions. Remember the picture from previously. Wouldn't it be great if we could reduce that? We could do something to the problem that moves our relaxation solution closer to the set of integer feasible solution. That would almost certainly help the solution process. There's two principal techniques for doing so. And those are presolving and cutting planes. And they are actually somewhat related to each other. Presolving are logic reductions of the model that you do before the main search starts. That will be the topic of my last presentation today. Now, cutting planes is about generating additional constraints that tighten the formulation. And there are three principles that occur at many places, both in cutting and in presolving. Three main ideas, so to say, that you see over and over again. Rounding. Exploit the fact that integer multiples of integer variables take integer values. If you see a statement about integer variables with integer coefficients and something says this could be fractional in the end, there's a potential for strengthening this. Lifting. Lifting is the idea of, well, fixing a certain variable in a constraint and then try to derive something from this. Make this constraint infeasible, make it redundant, and therefore either try to add this constraint to add this variable to this constraint or similar. And disjunctions, the obvious observation that binary variables always can only take one of two values. If you can make an argument about your problem for both the 0 case and the 1 case, then it holds in general, disjunctive argument. And you don't need to use the same reasoning in either case. We will see this a couple of times. I think this will become more clear throughout the presentation. Advice, if you ever try to work on presolving procedures, if you want to come up with new presolving deductions, start looking at cutting planes that were generated for your problem and ask yourself, why didn't I get this information that this cutting plane contains already in presolving? Okay, back to our MIP solver flowchart. Where are we? We are here in this tiny little extra loop inside the big time branch and bound loop, the cutting plane loop, inside which the general cutting plane method is executed. So this is the first algorithm that was presented for integer programming, Montgomery's cutting plane method. And again, we start with a colorful picture and a very pseudo code algorithm on the left-hand side. So what's the idea? We're optimizing over the relaxation over the set of linearly feasible solutions. We get a relaxation solution if that was in our integer feasible set. If this was integral, we would be happy. Well, this one is not. So we continue by adding a magic inequality to our to our description of the problem, an inequality that's valid for all points, for all integer points. So for this convex hull of the integer points, which we are trying to approximate via this algorithm, but it's violated by the solution of our linear problem that before. So an inequality, the border of an inequality is a plane. This cuts off, so to say, this point from this polyhedron, and it's a separation argument. It's a separating plane. It separates the points on the one side from the single point on the other side. So this is why we talk about cutting plane separation. Okay, so we did that, and then we just we repeat. We solve the linear relaxation again. It's still fractional. We, by pure magic, generate such a cutting plane added to the formulation. Loop again, and hooray, now the first ever integer solution that we found immediately will be the optimal one. So if you conduct the cutting plane methods all through the end, the first solution that you find is the optimum, unlike in branch and bound where you can find intermediate solutions. Okay, cool. We can stop the algorithm. And before going into the details of how we can find this magic inequality, I would like, as a little preview, tell you something about what different kinds of cutting planes there are. I like to separate them in general matrix-based cuts that you can derive for each and every mixed integer program out there. Most famously, Gomery cuts. We will cover quadri-Gomery cuts, mixed integer rounding cuts. Split cuts are the one that I mentioned in the bunch of bound talk. And then there are, in quotation marks, combinatorial, problem specific. Now the combinatorial is not in quotation mark, the problem specific. So this is not like for one single application that you as a user have, but these are for structures that are not there in every mixed integer programming that's out there in the wild, but in reasonably many of them, that it's worth detecting them, working with them, generating cuts for these particular structures, like knapsack constraints. You know, we saw in the modeling talk yesterday the knapsack problem, which has this single constraint, while these kind of constraints, together with many other constraints, appear in like half of the mixed integer programs that are in something like MIP or so, roughly. So using specific cutting plane techniques that work on these single constraints is a good idea. The second way to separate cutting planes is not about the way how you generate them, but where you generate them. So they are global cuts. These are cuts that are generated at the root node, and they are obviously globally valid for the remainder of your search procedure just by construction. And then there are two different forms of so-called local cuts. So you don't need to restrict yourself to generating cutting planes before you go into your branch and bound procedure. It's very often a very good idea to do it at intermediate nodes. And there you have to face a decision. When you generate cuts from local nodes in the branch and bound tree, you can either only generate cuts that are globally valid. These will have the advantage that you can reuse them at other parts of the search tree. You need to be careful to only use global information, like don't use the local bounds in that case. Only use the local solution, but not the bounds from which you derive your cutting plane arguments. Or you say, okay, that sounds like sketchy to begin with. I constrain myself to locally valid local cuts. Free to use, do whatever you want for generation there. I mean, as long as it's mathematical sound, of course. They're potentially stronger because they use more information, so that's good. But you'll not be able to reuse them at other parts of the tree. I try to illustrate this here. Yeah, you see, this is a valid cut for these 3 points, but over in this subproblem, it would cut off feasible solutions. So no. And this is a cut, even if you generated this from this solution, it does not cut off anything over here. Whether it's useful is a different question. Yeah. So generally, cutting plane generation, as mentioned in the beginning, works in rounds. So you solve the AP, you might remove some of the old cuts that you generated in previous rounds. You generate some new cuts, then you filter cuts and select cuts. I'm a bit nerdy here for making these distinctions. What I call filtering is you look at the individual cuts and say, okay, that the generation procedures have provided to you, and say, okay, this might not be a good cut at all because it's numerically bad. So I throw it away. I don't even consider it as a candidate. And cutting selection is having a set of candidates, not applying all of them, but making dedicated selection among them, because there might be some cuts which either of them is good individually, but if you combine them, they might not work as well. We'll see that later towards the end of the talk. I mentioned global and local cuts. At the root node, cutting planes are usually applied very heavily in the solver. You often have 20 rounds of cuts, so 20 times you loop through this procedure, sometimes more than 100. Inside the tree, locally, it's much less heavy. Typically not at every node, typically much less rounds, maybe only 1 or 2 or so, fewer cuts per rounds, all is dimmed down. Okay, so let's go into individual procedures for cutting plane generation. Matrix-based cuts, most famously introduced by this gentleman here before, the bunch and bound algorithm, the idea of the general cutting plane method by Gomery comes together with a recipe of how to generate these magic inequalities. Let's try to understand how this works. Okay, so assume we are given an arbitrary integer program. We have an optimal basic solution of its AP relaxation, just as the simplex algorithm provides us. Then the Gomery method will find for each of the fractional variables in the AP solution such a cutting plane. We add it to the relaxation rinse repeat. This assumes now for the next couple of slides that we are seeing our problem in the standard form AX equals B. And well, given that it's a basic solution, we use this basic representation of the solution. So I think we had this yesterday. So we have AX equals B. If we find a basic solution, we can compute the inverse matrix of the basic matrix. And we will call this entity over here B bar, I think. And we will consider this A, B minus 1 times A. This will give us one identity matrix. This is the basis inverse times the basis of the matrix, and then something which I think we call AN, most likely. No, A bar, excuse me. So then non-basic part. Okay, and the solution, as the simplex algorithm gives this to us, has all those variables that correspond to those columns at 0. And here, each of them gets the solution, has the solution of B bar. If you look at the drawings where we saw hyperplanes intersecting orphans, as one can see why this is exactly the case if you stare long enough at those pictures. Okay, so that's what we have. Our solution that we have is xi equals bi for the basic variables, xj equals 0 for all the non-basic variables, and we now just choose our favorite fractional variable xi, and look at this basic simplex tableau representation, a single line and a simplex tableau. B bar is not fractional. Okay, and we start massaging it. Let's try to walk through this and see whether we can do this. So first of all, nothing really happening here. We add a lot of zeros into this. So these cancels out, this cancels out. We will use this because we need to, in the next step, sort these values. So, but here, mathematically, we've only added zeros to both sides. So now we start sorting this. Everything that is integer goes to the left-hand side. So this part here is the integer part of B bar. We move it over to the left-hand side. The fractional part, which is B bar minus B bar rounded down, stays on the right-hand side. Same for the coefficients. We keep the A bar ij rounded down on the left-hand side and have the fractional part, A bar minus A bar rounded down. So that's the fractional part of this number on the right-hand side. Okay, still nothing really happened. We just reshuffled. So what we know, the equation that we get from a simplex tableau is like an aggregation of our original problem constraints. So aggregating problem constraints leads again to a valid equation. So for each integer solution, remember we did not start from an integer solution, we started from a fractional, but for each integer solution, the left-hand side here obviously must be integer because the xi and the xj must all take some integer values. Now some of them will be different from 0 and any integer solutions. Those are all integers. So the left-hand side must be integer. Obviously, the right-hand side must be integer. So somehow these values here will multiplied with some non-zero values in an integer solution will cancel out this fractionality there. We don't know, and we're not interested in how, but that's a valid statement. So since this is an equation, also the right-hand side must be integer. We know something more about the right-hand side. We can see that it is not only integer, but it's strictly less than 1. Why is that? So we started with a fractional variable. So this is the fractionality, which is strictly less than 1. All these values here are non-negative. So this is, fractionality is always a value between 0 included and 1 excluded. And those are non-negative variables. Not sure where I pointed out, but this is the standard form, has all xj greater equal 0. So okay, it's less than 1, and it's integer. So it's less equal 0. We applied an integrality argument. Okay, let's just carry this information over. There's literally no change between the last line of the previous slide and this line here. Okay, so the right-hand side must be less equal 0 for all integer solutions. Good. That I can express as an inequality. Yeah, right-hand side less equal 0. I just reshuffled this here again a bit. If this is less equal 0, then we get this inequality. Just brought things to a different side. This is a valid inequality for the integer program that we are looking at. And it's violated by the basic LP solution that we started at. Because the left-hand side here is 0, because all the xj are 0. And this is a fractional value. We round it down, we subtract the fractional value. So this is a negative value. So for the LP solution that we started with, this inequality does not hold. But we just argued for the last 3-4 minutes that this inequality holds for all integer solutions. So that's exactly what we are looking for. This is the Gomery cut. And then we add a slack variable, throw it into the system again, and continue. This is the Gomery general cutting plane algorithm. I recommend working through this once more, step by step. It feels like you cheated at some point, but you didn't. Okay, Gomery cuts proven. Let's move on and completely change gears here to a different type of cutting plane algorithms. They're called Gomery cuts. They don't work on the tableau, they work on the original matrix. They're only defined for pure integer constraints for pure integer problems. And the argument that we do here to derive a cutting plane is the following. We aggregate parts of the original matrix. So we do a convex combination, greater equal 0 lambdas. And then we do a couple of steps. So aggregation of valid inequalities gives a valid inequality. Then we round on the left-hand side. This is a relaxation of the original problem. So it's less strict. This inequality is less strict than this inequality. So it's valid and redundant. But then, given that now on the left-hand side, we only have integer entities, so integer coefficients, integer variables, we can also round down the right-hand side. That's on the linear space, that's a strengthening here. It's valid for all the integer solutions, and it might be stronger than the formulation you started with. Let's look at an example. So consider these two inequalities here. So this is the feasible set. So there's like values 0, 1, 2 here. Probably a bit hard to read, doesn't really matter. Okay, we start by aggregating then. My personal favorite coefficients for today are 1 over 12 and 1 over 12. So I feel like this, I just add these two inequalities with these two multipliers, checked out, 5 plus 7 over 12, that's 1, cool. 5 plus 3 over 12 is the same as 2 over 3, and 9 plus 9 over 12 is 3 over 2. Cool. Okay, so that's what we did here. We did a convex sum of these two, so this will go to the same intersection point as the intersection point of the two inequalities that you started with, and it will be redundant. Okay, first step of rounding. So I'm now relaxing this inequality here by rounding the coefficients down. 1 rounded down is 1, 2 over 3 rounded down is 0. So this gives this relaxed point here, this relaxed inequality, which is just a bound. And arguing with the integrality of x, I can now, or of whatever is on the left-hand side, I can now round down the right-hand side and see I suddenly get inequality which cuts off parts of the polyhedron I started with. Quatergomery cut. Okay, I was only partly joking when I said it's my favorite coefficient for today. I feel like this because you now, of course, immediately ask, well, but what kind of lambdas do you use in practice? And there's no best proven way of doing so. In a sense, you can understand the Gomery, well, using whatever brings you to the simplex tableau as one kind of such lambdas. And it's just a heuristic that you use there. There are many different heuristics. One that's particularly common and useful. An important special case is using only zeros or 1/2 as lambda. And you can show for many combinatorial problems that the problem-specific cuts that you could generate for them, you could also derive via as a 0, 1/2 cut from the general MIP formulation of the problem, like odd-cycle inequalities and whatever is listed here. So common heuristic, just use some 0, 1/2 values. Obviously, obvious generalization is mod k cuts, not as efficient as 0, 1/2 cuts. Yeah. Okay, let's come to the next class of general cutting plane algorithms. These are mixed integer rounding cuts or mirror cuts. We consider the mixed integer set here. I start, or a mixed integer set. I start with the really most basic variant that you can imagine. One variable integer, one variable continuous, and the equation that you have is just linking these two together with some fractional offset. So, and already in this case, these two, this inequality plus the bound of the slack, the continuous variable, do not suffice to describe the convex hull of the mixed integer set. So there's these tiny part here between this linear relaxation from these two inequalities and the actual convex hull. And I'll show you how you can close this gap by applying a disjunctive argument. So in the next line, we will first look at this part of the disjunction and then at this part of the disjunction. And I always found it a bit cumbersome to derive this straightforwardly. For mere cuts, I find it easier to start from the end, look at the final inequality, and then just check out that this is valid for either of the two sides of the disjunction. So the mere inequality is this one. And you can just check with pen and paper that this is, you can derive this inequality either by convexly combining 1 and 3 to each other, like rather here. So this 1 plus 3 with the correct coefficients as they are shown here will give this inequality, and you can derive the very same inequality with different coefficients from 2 and 4. The same inequality is valid for either side of the disjunction, so it's valid for the overall problem, disjunctive argument that you made here. So that's the so-called mere inequality. Okay. Then there's, well, generalizations. I might need to fast forward a little bit here. Essentially, it's pretty easy to generalize this to, first of all, not a single variable, but any a single integer variable, but any linear combination on the left-hand side. The equality essentially shapes just the same. Even more slightly general if you allow an arbitrary number of continuous variables, because essentially you could just aggregate them all into one, derive the mere inequality for this aggregation, and then move it again to the original form. And then you have complemented mixed integer rounding cuts, which is again a heuristic procedure. So what you do here is you divide your original constraint by some positive deltas, complement some of the integers, and derive a mixed integer rounding inequality for this. So generally, many classes of cuts are in effect complemented mixed integer rounding cuts of aggregations of the constraint matrix. We won't cover things like multi-commodity flow cuts, for example, but also there for a multi-commodity flow problem, you can take the huge amount of constraints that would model this, aggregate it in a pre-described way. There's an algorithm that suggests how to aggregate them to a single inequality, and then derive a mere cut from that. Okay, shall we try to do this? What's the answer to the first question? Hey, mixed integer rounding cuts rely on a disjunctive argument. Exactly. Question number 2. You 1/2 cuts are quadrigonometric cuts. Those work on an original constraint matrix. And finally, B, in MIP solvers, cut generation is typically applied aggressively at the root and moderately at some tree nodes. Cool, I'm proud of you. Let's look at structure-specific cuts, like the foreshadowed knapsack cover cuts. So those are defined for the feasible set of the knapsack problem that you all know and have seen previously. We talk about some of the logic of the knapsack problem. Namely, we define what a cover of a knapsack constraint is. It's a subset of the variables such that the sum of those are greater than the right-hand side. So a set of variables from which you cannot put all of them into your knapsack. Not all of them can be one in a solution for this problem. And then we can define a minimal cover. So a minimal cover is a cover, at no surprise, with the special condition that once you remove any of the items in your knapsack, it becomes feasible again. The set is not a cover anymore, minimal. And can quickly imagine that every cover can be easily reduced to a minimal cover. And the valid inequality, which can serve as a cutting plane that you can derive from this, is the number of items that you choose from a minimal cover of the knapsack is less or equal to the number of items in this cover minus 1. You can choose at most all but one for that. Let's look at an example. Knapsack problem. So I claim that the minimal cover for that one is the set 3, 2, 4. So is it a cover? 6 plus 2 plus 2 is greater than 8. So it's a cover. Cool. And as soon as I remove one of those values here, 6 to 2, the sum will be less equal than 8. So it's a minimal cover. And then obviously I can only choose at most one of, or I can set at most two of those three variables to 1. So that's the so-called minimal cover inequality. We didn't visualize it here, but it cuts part of the set that you would get from only looking at this single constraint. Okay, and then the procedure, how you do this in general MIP is you would check whether there are any violated minimal covers inequalities for each of the knapsack constraints in your mixed integer program. So in a sense, you're looking at a one-row relaxation of your problem. If you find something that's violated, add the minimum cover inequality and be happy. Okay, lifting. I want to do at least one lifting here. So let's try to lift cover inequalities. So the question that we try to answer with this slides full of formula is whether we can incorporate or whether we can add another variable x1 into our particular cover cut. We just do this by example here. So is there a feasible way of also adding x1? So reformulating this in general is there an alpha 1 such that in addition to our cover inequality, we can also add another variable alpha 1 x1. And this still stays a valid inequality for the feasible set of feasible solutions for the knapsack problem. And we do look at this via a disjunctive argument. Our x1 can take only two values, 0 or 1. The 0 case is simple because this works for every alpha. Okay, so we only need to look at the 1 case. Can we find a strictly positive? I mean, obviously for alpha equals 0, this would always work, but can we find a strictly positive alpha here, assuming that x1 equals 1, that this stays a valid inequality? Okay, so we formulate this, so enter the 1 into the equation, and well, we need to make this work for every solution of the knapsack problem which has x1 equal 1, so the maximum that this term can take here. And then alpha is just this right-hand side minus this entity here. Okay, so let's look at our example. This is the original knapsack constraint that we started from. We now assume that, or check out what value we get for alpha if we assume that x1 is part of the knapsack. So is equal to 1, then this is the right-hand side of this cover inequality minus the maximum that this form here can attend, given that x1 is in the knapsack, so the knapsack is less equal than 3. So this means we can use at most one of the variables. So this maximum here is 1, so alpha 1 is less equal 0. So this is a valid inequality for each alpha that's less equal 0. And of course, we choose the maximum one to get a strongest cut. Again, I recommend working through this slowly on your own, but that's a sketch at best of a lifting procedure. Let's look at the stable set problem now. Okay, remember from graph theory, what's the stable set? A stable set is a set of non-adjacent vertices. So in my example here, these three vertices are a stable set because they are not connected via any edge. So, and then a clique is a set of pairwise adjacent vertices. Like this is a clique in that graph. So for the stable set polytope, trying to, which is the polytope of all stable sets for a given graph, a valid inequality is that you say, obviously, for each clique in the graph, at most one of the variables can be part of each stable set. Okay, so like in, yeah, here, whatever a stable set is in the end, for our stable set, it's variable 3, but definitely not more than one of these 3 vertices can be in any stable set. Okay, so far, so good. Where do we have such a graph in a mixed integer program? Well, we can construct one as an auxiliary structure, because that situation that two things cannot be together in a solution, two binary variables cannot be one at the same time. That's a very common thing. And the logic of all such observations that you can make from your mixed integer program, these two variables cannot be one together. You can capture this as a graph, so-called clique graph, and then derive clique inequalities from that graph, because each solution of your MIP must be a stable set in this auxiliary graph when you think about it. So where can you derive such connections that two variables cannot be one at the same time? So for example, from assignment constraints. Yesterday, modeling presentation. Assignment typical structure, well, obviously, you could add an edge to your variable, to your clique graph for each combination of x1s here. But also from 2 elementary knapsack covers, as we just saw previously, or from probing often has such implications as a result, or even for constraints such like this. And you say, hang on, Timo, I clearly see how 2 variables must be one at the same time here. Yeah, but no 2 variables can be 0 at the same time. So this is like a clique on the negation of those variables. So MIP solvers would build up this clique graph not only having one vertex for each variable, but 2. One representing the original variable, one the variable -1 for a binary variable. That's what you call the complement or the negation of a binary variable. Okay, and then what you can do, as I just said, feasible solutions corresponds to stable sets in those clique graphs. So the stable set polytope of the clique graph, when you think about it, is a relaxation of the MIPS feasible solution, just by definition. Sounds fancy. You can try to find a maximal violated clique using your LP solution, and then generate a cut from that. So far for problem-specific cuts. Let's finally, another 2-3 minutes, we started with a little carryover from the first presentation, look into cut selection. What a luxury problem. We have a lot of cuts. All of these different procedures might have thrown in cuts into our pool. Which of these ones do we want to use? Well, I mean, the original cutting playing algorithm said using one is enough. This will provide you with a new relaxation solution. But then, of course, this will converge very slowly, as you can imagine. Okay, so let's do it the other way around. Every cut that we can find, we throw it into the LP. Well, so first of all, as we just argued, we don't need to cut off the solution multiple times necessarily. Cuts might increase the size of the model. So if you start with a model that has 10 constraints and already in your first round generate 1,000 different cutting planes, That does not sound like a good idea. And also the cutting plane separators themselves might be expensive. So there's a sweet spot in the middle. Balancing is important here. And that's why you do multiple rounds. So you, in a sense, refresh your LP solution in the middle of the procedure. And you always add only a limited number of cuts and might potentially throw out some old ones which have not been active for a couple of rounds. And you want to carefully choose which cuts complement each other nicely. And what means nicely here? So how does a good cut, a well-behaved cut look like? Well, it should be numerically stable, please. So not a too large coefficient range. This is a problem that Gomery cuts often suffer from. And this is one of those filtering criteria that I mentioned. You will throw away cuts that via lattice. It should be efficient or efficacious. The distance that we saw earlier. I will have some pictures on in a couple of, well, in 2 slides. So it should cut off really a large chunk of the polyhedron in a visual way. Ideally, it should be orthogonal to, or as orthogonal as possible to other cuts. If cuts are very parallel to each other, chances are that using more than one doesn't really give much benefit. And the next one is a funny one, almost parallel to the objective. Could be good. Exactly parallel is terrible because that will lead to dual degeneracy of your problem. You're shooting your LP solver and your branching rules in particular, much more than the LP solver in the lag if you add an exactly parallel cut. But then again, being similar to the objective function means together with this criterion that likely the dual bound will improve a lot. A lot of balancing going on there. Sparse cuts are good. And in the selection procedure, you will then aggregate different measures again into a single score, similar to what we saw for the hybrid branching scoring. And I will be closing here with a couple of pictures of what a good cut looks like. So that's a good cut. It's very efficient. It's very efficacious. It chops off a big part of the polyhedron. This one, much less. Orthogonality. So these cuts are all very parallel to each other. I mean, each of them individually might be a good cut, but they together is not a particularly nice set. These 2 cuts complement each other much more nicely. You see that they both, like, in a sense, go through the same point here, but the combined effect of these 2 is much more than the combined effect of these 5. My attempt to argue about the objective parallelism. So being completely orthogonal to the objective is not that great. You do cut off quite a significant amount here, but the objective change that you observe will be minimal here. This will be the new optimal solution here. So like the green one, for example, you will observe a really large step in the objective, but the red one is, again, is bad because it's exactly parallel. And sparsity is having less variables in the support here. So this is like a single variable cut. It's a 2 variable cut. Again, hard to draw in 2 dimensions, a meaningful picture. Hard to draw any picture in significantly more than 2 dimensions. I will skip over unit cube hashing. Okay, can we just close directly?